Children, so I hope all of you are doing great. Okay, so we'll start off with our session. So last session, we had solved all questions based on the topics that have been covered. So now we are positively progressing forward. Okay, moving on to the next aspect, the next chapter basically. So we have seen questions based on projectile motion. We learned about different types of projectile motion. We have solved questions based on that. Okay, so that is all we have done. So motion in a plane is complete. So on that note, we'll move on to the next chapter, which has again a greater weightage. So we'll move on to the next aspect. So the next chapter for the day is force, that is laws of motion. So we have laws of motion. Now laws of motion, I had started initially. So already we have looked at different aspects of laws of motion, but still we will go through some of the concepts. Let's have a quick recap before we dive into the questions or numericals. All right, so let me start sharing the screen. Just hold on, it's getting loaded. So my stylus is also getting loaded. I'll be sharing it in a while. So the screen I'll share, so maybe annotation will start in some time. So let me start sharing the screen now. You must be able to see in some time. It's loading. Yeah, here we go, children. I think you should be able to see it now. Okay. Screen is being shared. So this is all we had done in the last lecture. So now we are moving on to the next aspect. Okay. So here we go. So today's chapter, laws of motion. Yeah. So before moving into this chapter, laws of motion, so we try to understand certain basic concepts, some terminologies. Okay. So most of the terminologies you guys might be familiar with, but still, let's look at it. Let's have a quick run through. Okay. So I'll verbally itself or tell you what are the terminologies. So I'm just writing the basic aspects of it, not the entire definition. The first terminology that you have to know. So these are basic important terms, some important terms to know. Okay, so we'll see terms to know. So the first term that you'll have to be knowing is force. The first term, force. So all of us know what a force is, right? So force can be defined in simple language or in simple aspect. You can say force is a push or a pull that one object is going to exert on the other. Okay, so a push or a pull that one object exerts on another is basically force. Now what this force can do, okay, it produces, or you can say it tends to produce motion. So by applying force, you can set an object in motion. Is that true? Yes, of course, right? So you try to push an object by applying force, the object can move. So you're changing the state of rest of the object. Initially, the object would have been in the state of rest. As and when you apply force, the object can move. So by applying force, you can move objects. You can also change the shape or size of the object by applying force, which is called as deformation. So deformation, okay, is a classic example where you can change the shape or size of an object. Example, when you make chapati dough, okay, so what happens? You pour water in the wheat atta, and then what happens? You start kneading, right? So by kneading, you are able to change the shape and size of the object, which is your dough. Okay, so that is also possible by applying force. And what else can force do? Force can also change the direction of motion of an object. Example, in a game of shuttle badminton, when the opponent serves, okay, the shuttlecock, you can change the direction by using a shuttle, bat or a racket. So that happens by again applying force. You can change the direction of motion of an object. Same thing also goes with, you know, a batsman who is batting a ball. So by batting a ball, the batsman changes the direction of motion of the ball, which is again due to the force applied by the bat on the ball. Okay, that's an example. Next, what else can force do apart from this? The force can also stop a moving object, right? So by applying force, you can stop an object that is in motion. Example, apply the brakes to stop a vehicle or a car, automobile, whatnot. So force can be applied to stop a moving object. Okay. So these are the different aspects of force. Force can make an object move. Force can stop a moving object. Force can change the direction of motion of an object which is moving. And force can deform an object, that is, change its shape or size. So all this can be achieved by applying force. So this is all about the basic aspect of force and the applications of force. We have seen what are the different aspects of force. I hope that part is clear. That's the first term. The second term that you should know is the types of forces. What are the different types of forces? Okay, force and its types. Force can be categorized broadly into two different types. What are they? You can say contact forces and you can say non-contact forces. So these are two broad classifications of forces. Okay, so what is meant by contact? What is contact forces? Let's try to understand that. Contact forces are those forces that interact when two objects or surfaces are in contact with each other. Then you can say that it is a contact force. Okay, so we try to understand examples of contact and non-contact forces. Okay, so what are the different examples of contact and non-contact forces? First, let's look at contact forces. Friction is an example of contact force. You know that friction is an opposing force for objects in motion. So you can say friction. Friction is a contact force. Next, you also have something called as a tension force. Force which is going to be existing in strings when objects are suspended over it. Force experienced on strings, ropes, when objects are tied to it or fastened to it is a contact force. Okay, and you can also say applied force. Forces that are applied on certain objects to move them are again contact forces. These are all examples of contact forces. What about non-contact forces? Again, there are different aspects of non-contact forces. So we'll see what are the different types of non-contact forces. Okay, so examples, you can say gravitational force or gravity, because you drop a ball, you're going to release a ball from a certain height or an object from a certain height, the object will fall down due to gravity. Okay, because gravity pulls them downwards, non-contact. Magnetic forces. Okay, so forces experienced by system of magnets. When two like poles of a magnet try to interact, you can see that they repel, and when two unlike poles of the magnet interact, they attract. So magnetic forces. So you can say magnetic forces are non-contact. Apart from that, electrostatic forces also you can say. That is also a non-contact forces. So like this, you can give examples, children, of contact versus non-contact forces. Okay. So these are examples of contact versus non-contact forces. Okay. So these are some important aspects that you should know. Okay, the terms. So we looked at force, the types of forces now we have learned, and then the next terminology that you should be knowing is inertia. Some of you might be having an idea about what inertia is. Okay, inertia is a tendency by which an object continues to be in the state of rest or motion. You call that as inertia. The tendency where an object will be in rest or at motion. That phenomenon is called as inertia. Inertia can be of different types. You have inertia of rest, you have inertia of motion, inertia of direction. So there are different aspects to inertia. So inertia can be of rest, it can be of motion, and it can be of direction. So these are the different aspects of inertia. Okay, so that's all about inertia. So now we try to understand all these aspects with certain examples. Now, inertia of rest. We all encounter inertia of rest. Okay, for example, you sit inside a bus, and when the bus takes off, okay, when the bus starts suddenly from rest, what happens? We experience a forward jerk, right? A forward or a backward jerk. Obviously, it's going to be backward because when an object at rest accelerates suddenly, what happens? The lower part of the object is going to be in motion, but the upper part remains in the state of rest. Therefore, we experience a reverse back, reverse jerk, okay, or a backward jerk. So that is inertia of rest because we tend to be at rest, but the bus is in motion suddenly. Second, inertia of motion. The same example. In a moving train, what happens when it comes to rest suddenly? We all experience a forward jerk. Why? Because we were in motion and the train comes to rest suddenly. What happens? We tend to be in the state of motion for some time. Therefore, we experience a forward jerk. That's an example of inertia of motion. Inertia of direction. When a car takes a sudden turn, what happens? Passengers are jerked in the reverse direction of the turn. So a car moves towards the right, passengers get jerked towards the left. When car moves towards the left, we get jerked towards the right. So that is inertia of direction. This is experienced during sudden turns, okay, while navigating. So these are the different types of inertia that you will have to have idea about. Okay, so we have covered about the different terms. Okay, the important terms that you should be knowing. So on this, we'll move on further. Okay, so we have children different laws of Newton. So it's also called as Newton's laws. So most of you have some idea about Newton's laws, I suppose. You have Newton's first law, second law, and third law. So there is first, second, and third law of Newton. So there are different aspects or laws of Newton. So we'll try to visualize this. Now I'll show you an animation video so that we try to you can easily understand and correlate them with real life examples. Okay, so me just go to the animation window. Just hang on. I'm getting that ready. So we look at that. I'll be sharing that now in some time. Yeah, I'm sharing it now, so you guys should be able to see it. Yes, children. I hope it's visible now. Let's go through. Pay attention.
Imagine you're sitting on a recliner chair watching your favorite movie on a lazy Sunday. And your mom calls out your name and asks you to run some errands. You can imagine how difficult it would be for you to get up and do the work. Imagine you're practicing for your 100 meters race on this track. And somebody asks you to stop immediately within a second. Will you be able to do it? What if you're suddenly asked to turn towards the right? Will you be able to turn immediately? The answer to both the questions would be a no. You can stop, yes, but gradually. You can also turn, but not sharply. And guess what? It's the same story with every object. Every object will continue to do what it's doing. If it's at rest, it will remain at rest. And if it's in motion, it will stay in motion. But what can change this? Yes, only an unbalanced force can change this. If it's at rest and an unbalanced force acts on it, it will.
So here comes the concept of inertia. You can see the tendency by which an object can continue to be in the state of rest or motion. So you can see they gave a classic example where a runner or a person was running, right? So you ask them to suddenly turn or stop or change the direction of motion. It's quite not possible. That's because they continue to remain in that state. You can't suddenly change it. That's not possible. So therefore, here comes the concept of inertia. And when an object is at rest, you can see the example, first example on the left, which is green, highlighted in green. When an object is at rest, it remains in the state of rest. But what if you want it to move? You will have to apply some force, but that force has to be an unbalanced force. Now, this is very important. If you are going to apply a force that is balanced, there is no way the ball will move. Hence, an unbalanced force is required. Now, why do we call it unbalanced force? Some of you might be thinking. You can simply say force, right? Unbalanced force is important because whenever you see objects which are in contact with the ground, there is something called as friction that exists. So if you want an object to move, you will have to apply a force greater than the frictional force. And hence, it's crucial to apply an unbalanced force, which necessarily implies that a force greater than frictional force should be applied to make the object move. Okay? And that is the inference from this particular example. Okay? So with that, I'll again continue playing the animation. Please pay attention.
Move. If it's in constant motion and an unbalanced force acts on it, it may accelerate or change direction. And this is nothing but the Newton's first law of motion. Here's the correct definition. An object at rest stays at rest, and an object in motion stays in motion with the same speed and the same direction, unless acted upon by an unbalanced force. In simple words, it means that the objects continue to do what they're doing unless some external unbalanced force acts on them. We can also understand this using a simple diagram. If forces are balanced, there can be two cases. An object may be at rest, or an object will be in motion at a non-zero constant velocity in a particular direction. These can be the only two cases when the forces are balanced. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced. In the next video, we Do you remember the Newton's first law of motion? It says that an object will continue to do what it's doing unless acted upon by an unbalanced force or some net force. Now the important question is, what happens when there is net force acting on an object? That's precisely what the second law of motion will discuss. Do you remember understanding the first law of motion with a simple diagram? If the forces are balanced, the acceleration will be zero. In the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and in the same direction. Don't forget, these two cases will remain true only if the forces are balanced, only if the net force is zero. Now let's try to create a similar diagram for the second case. If the forces are unbalanced, then there will be acceleration. We saw that in the previous video. And now we come to the interesting part. Let's ask you a question, and I'm sure you can answer it. On which two factors do you think the acceleration will depend on? I want you to tax your brain a bit. Let me repeat my question. On which two factors do you think will the acceleration depend on? Okay, you apply a net force of 10 units on it. And then you apply a net force of 20 units on it. In which case do you think the acceleration will be more? Of course, the one in which the force was more. Depends on is net force. If it's more, then more will be the acceleration. If it's less, then lesser will be the acceleration. Acceleration depends directly on the net force. Come on, now I want you to think about the second quantity the acceleration will depend on. Let's say there are two objects on the table. One has a mass of 3 kilograms and the other has a mass of 5 kilograms. Now, if you apply net force of 10 units to each of them, which one do you think will accelerate more? In simple terms, the acceleration is directly proportional to the net force applied and inversely proportional to the mass of the object. That's the second law. Or as more people understand it, like this. The net force is the product of mass and acceleration. With this, can you tell me the units of force? That should be easy. The standard unit of mass is kilograms, and that of acceleration is meters per second squared. So the unit of force is kilograms times meters per second squared. And this is what we call as Newton. 1 Newton is 1 kilogram times meters per second squared. So if the mass of the object is 10 kilograms and the acceleration is 10 meters per second squared, then the force will equal 100 newtons. We can say that 1 Newton is defined as the amount of force required to give a 1 kilogram mass and acceleration of 1 meter per second squared.
So this is all about the Newton's second law, where it relates force, acceleration and mass. So we try to understand how force is going to change if the acceleration is going to be increased or decreased based on the given scenario. Again, by applying greater force, what happens to the acceleration in that case? So vice versa, you can try to understand, because mass always remains constant. So on that note, so we are moving on to the next aspect, that is Newton's third law. Also we will see. Okay, second law, first law of motion is done. So now we'll move on to the Newton's second law of motion, which is force relationship, and then third law. Okay, now we'll see the third law. Let me load that. So I hope it's visible now.
The only question you need to ask yourself while studying the third law is, what happens when two objects interact with each other? What happens when you place an object on the table? The object exerts a force on the table, and the subject exerts an upward force on the object. There are two forces that result from this object. The magnitudes of the two forces are the same, but the directions are opposite. These forces are called as action and reaction forces. The force exerted by the object on the table was an action force. What we saw here is action has an equal and opposite reaction. That's how simple the third law is. Every action has an equal and opposite reaction. It means that when two objects exert a force on the first object equals the magnitude of force on the second one. And what about the direction? The direction of force on the first object is opposite to the direction of force on the second one. Let's talk about more examples. While a frog is swimming, it pushes the water back, and the water pushes its body forward. Now let me ask you a question. Say a bird is flying upwards. The third law is not so obvious. You'd probably say that the bird is the only object here. The wings of the bird push the air downwards, and the air pushes the bird upwards. Action and reaction forces make it possible for birds to fly. We take one last example to understand something very interesting about the third law. What happens when a gun is fired? You're right. It exerts a forward force on the bullet, the gun. And this exists in recoil of the gun. A perfect example of Newton's third law. But hold on. If the force exerted by the gun on the bullet is the same as the foil with the same acceleration at the same acceleration as the bullet, right? Same magnitude of forces, but different accelerations. Why do you think this happens? Okay, so if your concept of the second law of motion was clear, you wouldn't really be surprised with this. The second law of motion says that the force is the product of the object's mass and acceleration, or the acceleration of the object is equal to the force over its mass. What does this tell us? Yes, if the mass is more, then the acceleration will be less. In this example, the mass of the gun is much more than that of the bullet. Hence, the acceleration of the rifle is lesser than that of the bullet. If you're in a boat and step out of it onto the land, there are two forces involved. You pushing the boat behind and the boat pushing you forward. And that's why you see the boat go behind when you go forward. Now let's say a sailor jumps off a huge ship. The sailor does apply a force on the ship, and the ship also applies a force on the sailor. But do you think the ship will accelerate as much as the sailor? Not really. And I think you know why.
So based on this, so the concepts of Newton's first, second, and third law, I hope you understand you can able to correlate them with real life examples as well. So that's the reason, that's the agenda behind showing the animation. Okay, so with this animation I hope you are able to correlate. So now we are moving on to do something more even interesting. So we look at the simulation. We'll try to simulate and we will try to learn by simulation. Okay, so I'm moving on to that particular tab. So I hope the simulation tab is now being shared and you're able to see it. Okay, so we'll try to understand this simulation. Okay, so we try to understand forces and its motion, how forces are going to interact, okay, with each other. So let's try to simulate and then try understand them in real time. Okay, so on a real time basis, what is going to happen is what we try to understand via simulations. It's a greater way of understanding any concepts, so that you can correlate them with real life situations as well. So on that, we'll look at the first simulation. This is for net force, children. I hope you're able to see it. Okay, so you can see net forces wherein you have two different teams and there is a cart in between. Okay, the cart is having a lot of goodies. You have a lot of chocolates and the team that wins is going to get the chocolates. So we'll see how it works. Okay, so you can see that there are three different parameters which are there for comparison or comparative study. The first one is sum of forces, second is values, and third you have the speed. Okay, so I'll be revealing one by one, in each and every aspect. So you have two teams, blue versus red. Okay, so now what I'm going to do is basically I'm going to select a person with a blue team. Okay, and I'm going to place him here. Now you can see as the blue team person is ready, there is going to be some force associated with the blue team's person. Okay, so I'm going to even take another person from the red team. Okay, now you can see that I have selected two persons, one from the blue team and one from the red team. And now I'm going to show you the values, okay, of the forces. Fine. Now, if you see the values of the forces have been given, the blue team guy is going to exert a force of 100 newtons, while the red team guy is exerting a force of 15 newtons. Now, in which direction will the cart actually move? So we'll try to understand this. There is going to be some net force or not? In this situation, anybody? Will there be a net force that is going to act, and in which direction will it act? So, and can you tell me what is the value of that net force? Anybody? Based on the blue and the red team? It's quite evident, right, from the figure? Any idea? The left side force is, yeah, yes, it is 50 newtons is the net force, and it is on which direction?
Right.
Yeah, it is on which direction? I was asking. 50 newtons net force is right, but on which direction? On the left or the right?
It is on left side.
Yeah, it is on the left side. Now let us see which team is going to win. You can see because 50 newtons force is on the left, and therefore the cart moves towards the left and the blue team wins. Okay, so by this way, you can easily understand how net forces actually act. Now what do you think will happen? I'm going to replace him with a red team and I'm clicking on go, but the cart does not move. Why it does not move in this particular case? Again, we try to understand from Newton's laws, gives us the answer for this, right? So the reason here is, you can see the net force is going to be 0. Okay, plus 100 on the right side, minus 100 on the left side. So net force plus 100 minus 100, cancelling out gives you 0, and therefore the cart does not move. So the net force is 0. Okay, so that's the aspect. That's your learning process, and that's how you understand what's happening in real time. Now, what happens if I'm going to give an additional, a person on the red team? You can see there is an net force, and the red team has won. Okay, so this is how you can understand the concept of net force and the Newton's laws, also how the object moves under the action of an applied unbalanced force. Okay, so this is the demonstration for that. Now look at this. Okay, look at this. Now you have a person. So a person is applying some force on the cart, and you can see that the cart is moving. It continues to move, and then it is released. So an object in motion continues to stay in the state of motion. So this is the demonstration of Newton's first law. An object at rest will remain in the rest. An object in motion will remain to be in the state of motion. Okay, so that's the aspect. See, again, let us push him. Now this time a greater force is applied, and then it is left. So you can see the object continues to be in the state of you know motion. As simple as that. Okay, and that is the aspect. Now you see what I am doing. So let me push the object again. So I'm applying a force, and then it is left, and then we are placing another object on the top. See, and still it keeps moving. A refrigerator is placed on the block, and still it keeps moving, because the object in the state of motion continues to be in the state of motion as per Newton's laws, because you don't have any external unbalanced force. The moment I'm going to place the fridge here in front of it, then what happens in the pathway? Then it is going to stop. So we'll look at that also. Okay, here people are there. Person is standing. Okay, and he's also holding a dustbin. Okay, you keep adding people there. So and then you try to understand what's going on. Okay, so like this. So it's easy for us to understand. So when we apply the forces again, see here, a force is applied, but only when your applied force should be unbalanced force. Here you see it is less. Still I have not got. That's why it keeps moving. Apply. The moment you reach that particular force, then only the object is going to come to rest. Eventually it will come to rest. Okay, see, now it came to rest, because the force is going to be unbalanced. That came to rest, and then now it starts moving towards the left. So this is a classic example to understand Newton's first law of motion. See, so by visualization, illustration, and demonstration, by using simulations, it's very clear for us to understand and correlate the concepts. So now we'll move on, children. So I hope this aspect is also clear. Next, we talk about friction. Okay, so what do you mean by friction? How can you see for the previous aspect and this aspect? Previously there was no friction. Now here there is a friction. Okay, so again the person is going to apply a force, and the object, you can see there is a frictional force. By default, can you see there is a frictional force arrow mark? Okay, so when the applied force is greater than the frictional force, this much frictional force is there. Okay, see, even now force is applied, it does not move. When it starts moving, when the force is greater than the frictional force, it moves. You apply more force, only then the object moves. And I release this. What happens after some time? The frictional force is acting on the object. After some time, the object is going to come to rest. Can you see? Slowly it comes to rest and it stops. Why it stops? Because of the friction. Now again, let me push the object. So the object is being pushed now. Again, 500 newtons of force is applied, but I want to stop it. So what I'm doing, I'm increasing the friction. See, friction is increased. When friction is increased, what happens? The object comes to rest. Okay, so we apply. Now sum of forces are 0. That's the reason it came to rest. Okay, so we try to apply the force now. You can see applied force. Again, frictional force is not overcome. The moment frictional force is overcome, only then the object will move. Until then, the object will not move. Okay, so this much frictional force is there. So precisely frictional force is 290. Appropriately, the value. So I'll put the values also. So 188 newtons is the frictional force. Okay, you can see it's 1 149, 150. So appropriately you keep increasing the applied force. The moment it is greater than 188 newtons, which is a frictional force, the object will start moving. So that is what you need to understand in this particular case. Okay, so an object is also. Now you see when the person is sitting, the frictional force is increased, right? See, it is increased. So the applied force and both the frictional force both are equal. That's the reason the object is not moving. So let us reduce the frictional force. Here applied force is 500, frictional force is 257. Okay, and therefore the object moves. So like this we can understand. Now what happens if I'm going to give the refrigerator to the person who is sitting? What do you think will happen? Frictional force will increase. Then, because there is more weight exerted and therefore frictional force is greatly increased and the object comes to rest. Okay, so this is the aspect that you need to know. When friction is there and friction is not there, what happens? When I say there is no friction, then it starts moving. No. So that's the aspect, children. Okay, so masses and everything, you can look at values, you try to understand. Okay, so all the aspect. So this is all about the frictional force. So when there is friction, what happens? We try to investigate. Next, moving on to the last simulation. So here you can see we try to understand whether the object is going to accelerate or not. Okay, acceleration. Also let us look at, so again here there is a sudden change in velocity of the object. So the object is going to be in motion and the object is moving like this. Okay, so it starts moving. Then you place a tub of water. What happens? The object starts to slow down eventually. Okay, the person also sitting over the tub of water, again you can see what happens to this particular object. So you can try to investigate this in different ways and then you can correlate. So that's the aspect of simulations. So okay, so in a different scenario you put different situations and you try to study the effect of forces in different aspects, so you can easily understand what the concept of net forces, motion, friction and acceleration is all about. Therefore the Newton's laws are clearly evident, which is applicable to each and every scenario here. So that's all about the simulations. So on that note, we'll go back. So these are the different simulations, children, that you will have to understand. So let me go back now. We look at different aspects of Newton's laws. So let's go back and we'll try to understand an important aspect now through an animation. So moving on to the next topic, children. Okay, so we are having a recap of what we learned in the last class. So already this was taught long back. So what we are doing is we are doing a quick recap. For this, notes also have been already posted. So you can check back in the WhatsApp group. So we look at the next animations which are there. Just hang on, children, getting it ready. here we go to the next aspect. So I hope you're able to see it now. So this is all about children free body diagrams. So we'll try to understand what are free body diagrams in this particular animation video. So here we go.
I want you to read these 5 situations and draw free body diagrams for each. Okay, so let me draw the first one for you and then you can try the rest. Let this horizontal line be the top of the table and the box is placed here. The free body diagram shows all the forces acting on it. First, there is a force of gravity acting on it. It will be downwards. And then there's a normal force acting upwards. As the forces are equal and opposite, the box does not move at all. It continues to remain at rest. And also notice that the size of the arrows is the same. The forces are balanced and the net force is 0. Now why don't you try drawing the free body diagram for the second situation? Read it well. First things first, the force of gravity will exist and pull the box in the downward direction. As it's placed on the table, there will be an equal and opposite normal force acting upwards. Now we come to what's written. A rightward force makes the box move across the table with rightward acceleration. The word acceleration is very important here. It means the velocity is changing, and the fact that the velocity is changing implies that the forces on the box are unbalanced. The upward and the downward forces net each other off. What about the leftward and the rightward forces? Now because there is a rightward applied force, we show an arrow towards the right. Will there be any leftward force on the box? As we've been asked to ignore air resistance, it will only be the force of friction acting towards the left. And because the box is accelerating towards the right, it means that the force of friction is lesser in magnitude than the applied force towards the right. And hence the size of the arrow of the applied force is bigger than that of the frictional force. The third situation is extremely interesting. Try making its free body diagram. It says that the box is moving at a constant velocity towards the right. In any case, there will be the gravitational and normal forces acting on the box, but this time, the applied force and the frictional force will be of the same in magnitude. Hence, the size of these two arrows will be the same. As the net force is 0, the body will continue to move at that constant velocity. And don't forget, we've been asked to ignore air resistance here. Now, would you like to try drawing the free body diagrams for the fourth and the fifth situations? In the fourth case, let us first discuss the forces that are acting on the skydiver. There will be the force of gravity which is pulling the skydiver down. As there is no table or ground, the normal force will not exist. And there's no applied force on the skydiver either. But as the skydiver is falling at a constant velocity, it implies that the net force must be 0. Which is the force that will net the force of gravity? Yes, it will be the air resistance. As the velocity is constant, it implies that the magnitudes of these two forces are equal. This is the free body diagram of the fourth situation. I want you to get the fifth one right now. This is how it will look. As it's free falling, it means it's accelerating. So the magnitude of the gravitational force will be more than the magnitude of the air resistance force. With this, you've understood the basics of forces. To know more, do watch our other videos.
Yeah, so I hope the concept of free body diagrams you're able to understand through this animation videos. So whenever you have an object that is placed on the say table, then what are the forces that are going to act? So weight of the block is going to act vertically downwards. Okay, you have a reaction force that acts vertically upwards. So these are the different aspects you should know for the forces. So on that note, so now we have covered the different aspects of forces. So we looked at what are free body diagrams, we discussed Newton's laws, and we have seen different situations of Newton's laws by animations, and we also understood the concept of Newton's first, second, and third law via different applications, and we have learnt about the different aspects of the forces that can exist in nature. What are different types of forces and where do they come into picture? So here today's session has been different aspects of forces, and that is going to act across different objects, and what are the different accelerations that it can produce. So on that note, we will see some examples also. Okay, so let me come back to the blackboard and let me again represent it here. Yeah, here we go. So going back to our notes, so that is being presented now, so I hope you're able to see it right now. Okay, so here we look at the aspects of the different three body diagrams that we saw in the animation video. Let's have a quick quick recap before we wind up. So here comes the first one: a block placed on a horizontal surface. So, okay, what happens when a block is placed on a horizontal surface? So here we are learning free body diagrams. So we look at different free body diagrams. What is there? What are the forces acting when a block is placed on the horizontal surface? Let us look at it without any further delay. So I'm taking a horizontal surface. So this is the horizontal surface. Okay, and I'm going to place a block over it, as you see. So this is the block that I'm placing, and what are the forces that are going to act with respect to the block? You know that gravity is going to pull it vertically downwards. Here weight component will act, which is m into g. At the same time, to balance it, there is going to be a reaction force that is going to act vertically upwards. Okay, n is called the normal reaction. Mg is your weight, n is the reaction force or normal reaction force. Okay, these are the forces that acts on the block which is placed on the horizontal forces. And what is the relation? You can see both are equal and they are opposite, so you can say n is equal to mg, and that's the relation that you get in this first case. Okay, when a block is placed on the horizontal surface. Quite simple. Second aspect, well, let's look at the second scenario as well. Okay, the second situation: a block is pushed towards right by applying force, by applying some force. So you're trying to push it. Now here, if there is a condition, they're asking you to ignore friction. You need to ignore the friction. So in that case, what happens? You show the horizontal surface first. Then you place a block. Place the block here. Now we have an applied force. See, there is a force that is going to be applied. Let's call it as force F. When the force is applied, what happens here? It tries to move towards the right, isn't it? And you need to understand that there is a frictional force. And if it has to move, and what is the condition? If the block is moving in spite of friction that exists between the surfaces in contact, you need to understand that applied force is greater than frictional force, and only then the object will move. Okay, so these are the forces that are acting. At the same time, you have normal reaction force acting on the top, and you have weight also that is acting downward. So in free body diagram, we'll show all the forces with respect to a common point. Okay. So let's take the center of the block as the green point. With respect to the green arrow mark, you show all, green point, you show all the forces that are interacting. So your applied force F is going to act towards the right. Frictional force is acting towards the left, opposite to the applied force. Normal reaction force acting vertically upward. Weight acting vertically downward. Okay, that's it. The condition is applied force is greater than frictional force, and the object tends to accelerate towards the right. So in this case, what happens? What is the formula that you can write? Okay, for acceleration. Now, children, you need to understand an important aspect here, that is horizontal and vertical plane. Now look at the horizontal plane. I'm using horizontal plane. I'm representing it using an orange dotted representation. So this plane is called horizontal plane. Force is acting along the horizontal. Okay, called is the horizontal plane. And you can see force is acting along north-south direction. Okay, that is the vertical plane. East-west direction horizontal plane, north-west direction vertical plane, north-south. Okay, so that's the aspect. So this is vertical plane. Simple. So we understand what is horizontal and vertical. Now you apply the equations of motion and then you get the relation for horizontal and vertical plane. Now in vertical plane, when you apply the equations, what happened? You can see N is equal to mg. Direct you will write, because there is no acceleration involved in the vertical plane. There is no motion in the vertical plane. But along the horizontal plane, there is motion. Why? Because your applied force is greater than the frictional force and the object begins to move towards the right. So therefore, in the horizontal plane, you can see there is an applied force, and so you can simply write applying Newton's second law of motion, which tells you F net or net force is equal to mass into acceleration. What is the net force here? Applied force, which is capital F, minus frictional force on the left. So F is equal to mass into acceleration. And now you can write the expression for acceleration as A equals applied force minus frictional force upon mass. And that is the answer for acceleration for the given scenario. This is how you find out the acceleration. Okay. What about frictional force? How can we else write frictional force? You need to understand frictional force can be expressed as the product of mu times n. What is mu? Mu is called the coefficient of friction depending on the surface in contact. Okay? So mu is coefficient of friction, and n is called normal reaction. This already we learned. Okay, and we also know that n is equal to mg. Since n is equal to mg, what is your frictional force? As F is equal to coefficient of friction mu times n, you can write it as mu mg. Okay, so it can be expressed as mu mg. So that's the frictional force. Go and substitute children back in the expression of acceleration. And what do you get? You can write acceleration as F minus mu mg divided by m. Okay, so this is the expression for acceleration in terms of coefficient of friction. Okay, mass and the acceleration due to gravity. You go substitute it and then you can get the expression like this. So all of them are one and the same. Here we have expanded and we have expressed it. That's it. Okay, so like this you have different scenarios. Fine. So we'll see this also. So we have covered it long back, but still we're having a recap. So I insist all of you to go through the notes, previous notes, so that you're able to correlate. And then we can solve different aspects of different questions based on this case, okay, of free body diagrams. So on that note, we can wind up. So any doubts, children, you can definitely ask. You can get it clarified. I hope you understood today's lecture. We did a lot of animations and simulations, so that it's easy to correlate and understand the concepts. So that's important. Okay, and then we'll do the solving of the questions. Now solving should be very easy for you, because you're able to apply them based on the given situation. Okay, so that is the main agenda behind illustrations and simulations and animations for today. Okay, so with that we can wind up. Any doubts you can ask. Now the forum is open for doubts clarification. Anybody have any doubts, you can ask. Please refer to the previous notes as well before coming to the next lecture. It will help you a lot. This next lecture we have questions. Okay, welcome.
Thank you, sir.
Yeah, you're welcome, dear.